Hi everyone, welcome back. You're watching the ninth lecture of EE 635 Applied Linear Algebra. This happens to be the third and final module. So in this lecture, we have been looking at this idea of inner products, which are generalization of the idea of dot product that we see in R3. We have abstracted the essential properties of an inner product, and we have used them to define the abstract idea of inner product over an abstract vector space um, with scalars coming from either real numbers or scalar or complex numbers. Now, using that idea of inner product, we have seen that we have this, corresponding idea of norms or lengths of vectors, right? And then using that idea of norm and inner product, we have defined this idea of orthogonality of vectors. And with that, we have seen what we mean by an orthogonal set of vectors or orthonormal set of vectors. We have seen that an orthogonal set, also orthonormal set, is always linearly independent, right? And then using this amazing idea called Gram-Schmidt orthogonalization, what we have found out is that if we have a finite collection of vectors, then say v1 up to vn, then we can construct an orthonormal set of vectors w1 up to wn such that span of v1 will be span of w1, span of v1 v2 will be span of w1 w2, span of v1 v2 v3 will be span of w1 w2 w3, and so on. Yeah, and then as a special case, it follows that for every finite dimensional inner product space, there will always be an orthonormal basis for that vector space. So remember, every finite dimensional inner product space will always admit an orthonormal basis. Yeah. Examples are plenty. For example, like think of Rn. Think of the standard basis vectors E1, E2, E3 up to En. That's an orthonormal set. You can check easily that EI dot product or inner product EJ is always equal to 0 if I is not equal to J, and EI norm is equal to 1. But that's not all. There could be many other uh, orthonormal basis vectors also. Yeah, like for example, just take any arbitrary basis, some v1, v2, v3 up to vn, an arbitrary basis, arbitrary linearly independent set of vectors, yeah, in Rn. Then run Gram-Schmidt orthogonalization on it. That will give you an orthonormal basis, which will not just be any old orthonormal basis, but also the added property that it's any subset of that basis is also an orthonormal basis for that corresponding subset of v1 up to vn, the subspace that is spanned by that subset of v1 up to vn. Yeah, so in fact, span of v1 will be span of w1, span of v1 v2 will be span of w1 w2, span of v1 v2 v3 will be span of w1 w2 w3, and so on. Okay, right. We have also seen in the process that when we have an orthonormal set of vectors, then expressing other vectors in terms of those, in terms of linear combinations of those orthonormal basis vectors is very simple. Yeah, in fact, the coefficients. So suppose I have, suppose I have v1 up to vn, which is an orthonormal basis. Then alpha 1 v1 plus alpha 2 v2 plus dot 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 up to alpha n vn. These alphas, so if that linear combination is equal to v, then these alphas are in fact, alpha 1 is v inner product v1, alpha 2 is v inner product v2, alpha 3 is v inner product v3, like that. So just have this vector, you have to express them in terms of linear combination of the orthogonal basis vectors. Just look at the projections. That's it. Great, no? It turns out that this taking projection business has a more profound consequence. not just this. The consequence is that suppose my vector v is not in the space spanned by some orthonormal vectors, but rather outside. But then I want to approximate this vector v by some linear combination of vectors in this subspace, for which I have this orthonormal basis. Yeah. Then that best approximation is also given by that projection. Intuitively, the idea is very clear. Like, for example, in R3, suppose I have a subspace and I have some vector. I want to get the best possible approximation of that vector on that subspace. How do you get it? Just do an orthogonal projection. Yeah, that will give us the error to be orthogonal. And that says that, because if there is a plane and there is a point in space, and I'm trying to drop a line from that point on that subspace, on that plane, the line with least length that can be dropped from that point onto that plane, that least length line must be the line that is orthogonal to this plane. Yeah, that's the error, and that is error. If that is the error, then the vector that I get on that plane, which is such that this plus the error is equal to the original vector, then this vector on the plane is the orthogonal projection. And that happens to be the best possible approximation because the error is the smallest there. But it turns out, surprisingly, that this very intuitive, very geometrical idea that is true for R3 actually works out for any inner product space. That is what we will see now. Okay, let me share my screen. Right. So as I said, over R3, the idea is very clear. So the topic that we are going to discuss now is best approximation the idea is, okay, so, okay, and suppose, suppose this is the plane that I'm interested in, say so this x, y, z, so this is the xy plane. And suppose there is a vector here. What is the best approximation of this vector here? Well, just drop this perpendicular. This is the best approximation, the orthogonal projection. Yeah, and the orthogonal projection has the property that this angle is, this is an orthogonal. This is 90 degrees. Yeah. How do we extend this idea to the general case of general inner product spaces? Okay. Now, how do I get this? For the general case, how do I get this best approximation? In order to do that, in order to formalize this idea, I have to make sense what I mean by best approximation. So, so let V together with this be an inner product space. Yeah. And suppose W is a subspace of V. Okay. Then a vector and let V in V be an arbitrary vector. oops, be an arbitrary vector, right? V hat in W is called a best approximation of V in W if for all W in the subspace W we have, notice carefully, V minus V hat norm is less than or equal to V minus W norm. Quite intuitive, right? Intuitively obvious, the definition that a vector in the subspace W is called a best approximation if for every vector in W this length is less than or equal to this length. Yeah, so what this says is that, okay, suppose this is my subspace and this is my vector V. Now this V hat here will be called a best approximation if for every other W in this subspace, W1, W2, whatever vector you may take, these errors, these lengths will always be greater than or equal to this error length. Then it's the best approximation. See, this is the error. So if W, I purport W to be an approximation, then V minus W norm is the magnitude of the error. V hat, with V hat, the magnitude of the error is V minus V hat norm. So V hat will be the best approximation if it's the length corresponding to the error for V hat is less than or equal to the error due to any other vector. Yeah, notice here that grammatically it's a bit weird to call it a best approximation, because we often say the best, right? Because best is superlative and superlative is supposedly one. But here at this point, it's not yet clear whether this V hat is unique. There could be multiple such best approximations. That's why we are saying a best approximation. Right? Is that okay? Now, the question is, how do I get this best approximation? So, okay, so here is the thing. So first we state this theorem. So the setting is the same. V is an inner product space. Let V in V be arbitrary. Then, okay, arbitrary, and let W in V be a subspace. Notice that nowhere have I assumed that these are all finite dimensional. I don't need them to be finite dimensional. They could be infinite dimensional as well. It's just that they have to be an inner product. V has to be an inner product space. Yeah? W is a subspace. Then V hat in W is a best approximation. I'm not writing of V in W, it's understood. Best approximation if, see, this is the beauty, if and only if V minus V hat, the error, inner product with W is 0 for all W in W. Recall that this is what we say that this V is orthogonal to W for all W in. I mean, these two statements are in fact equivalent. Saying orthogonal is the same as saying that the inner product is 0. Yeah, this is profound. First of all, why should this be true? This is true for R3, we understand that. But for in general, for an infinite dimensional inner product space also, this would be true. And not just that, what is what this tells us is that, you see, this definition of a best approximation is immensely difficult to verify, because in general this subspace W will contain infinitely many vectors. So even if somebody gives me, okay, take this vector in W, call it v hat, and I claim that this is a best approximation, how do I even verify that? In order to verify, I have to check this, I have to do this, do this checking of this inequality for every possible W, and there could be infinitely many W, small w vectors in capital W. So it's practically impossible to check this condition. However, this is kind of not very difficult. Yeah, it's much easier than checking for all possible vectors W. Although here also we have all possible vectors W, but as we'll see very soon, that, for example, suppose W was finite dimensional, then I just have to check this on the basis vectors. That's it. Yeah, by sesquilinearity property of inner product, if this inner product is 0 on a basis vector, every vector of the basis vector, then it would be true for every other vector in the span of those basis vectors, right? So therefore, this checking is much easier. But then the question remains that why should this be true? Why should this error being orthogonal to every vector in the space, in the subspace W, be necessary and sufficient for that vector to be a best approximation? So that is what we'll prove now. It turns out that this is the first part of the theorem. Yeah. So I'm calling it part 1. Part 2 and part 3 is coming up, are coming up. We'll see them very soon. Now, here is the thing. Why should this be true? How do we prove this? So it turns out that one direction is simple, the other direction is difficult. Yeah. So first we prove the if direction. So here we assume that V minus V hat W is equal to 0 for all W in W. This is what we're assuming. We have to show that V minus V hat, okay, not this one, V minus V hat the norm, V minus V hat norm is less than or equal to V minus W the norm for all W in W. And the trick is very simple, in fact. So what I notice is the following. So let W in W be arbitrary. Yeah. This norm VW, notice that this can be broken, this can be written as V minus V hat plus V hat minus W. I've just added and subtracted V hat. This, however, is by that sesquilinearity property, this V minus V hat. So I have to put the squares, huh? Yeah. This is V minus V hat squared plus V minus V hat minus W, yeah, plus plus V hat minus W, V minus V hat, plus V hat minus W square. I just expanded out. This is just inner product of this guy with itself. That is what I have expanded here. Yeah. Now, this is what v hat is a vector in W which satisfies the property, and W is an arbitrary vector in W. So this obviously implies v hat minus W is in W because W is a subspace. All right. So then this must be 0 by the property. This is just the complex conjugate of that. This must also be 0. Yeah, if the inner product VW is 0, then WV inner product also is 0. So then what this means is that V minus W's norm is equal to V minus V hat norm square plus V hat minus W norm squared. But this is a norm squared, right? So this quantity is bigger than or equal to 0, which obviously means V minus W whole square must be bigger than or equal to V minus V hat square. Yeah, which is of course the same as saying V minus W is bigger than or equal to V minus V hat, which then means V hat is indeed a best approximation. Yeah, so if direction is proved thus, we have to prove the only if direction. That is actually a little more involved than this one, so you have to pay much more attention. So let's see what's happening here. So here for the only if part, what we're going to do is we assume that V hat is a best approximation, that is V minus V hat is less than or equal to V minus W for all W in the subspace W. We have to show that inner product of V minus VW with a W, V minus V hat is equal to 0 for all W in W. That's what we have to show. Okay. Now, once again, we start with that same trick. We say that V minus W, this norm squared, is the same as V minus V hat plus V hat minus W norm squared, which is the same as V minus V hat square plus, I'm going to write it directly, 2 times the real part of V minus V hat minus W plus V hat minus W whole square. Yeah. Now, because it's a, this implies 2 times real part of V minus V hat minus W plus V hat minus W whole square. This is equal to V minus W square minus V minus V hat square. But see, this is a best approximation we have assumed. So this quantity is bigger than or equal to this quantity, which would mean that this difference is going to be greater than 0. So this is bigger than or equal to 0. And this is true for all W in W. Now we are going to do a modification, and that is very important. You have to pay close attention to what I'm doing here. What I am saying here is that when I'm saying that take all possible W in W and I'm putting V hat minus W here, notice that this set of V hat minus W, where W is varied over all of W, this set, notice, is the same as W, because W is a subspace and V hat is a vector in that subspace. What I'm saying is, say, okay, in R2, suppose I have this line as a subspace, and then I fix a vector in that subspace. And then I say that look at all possible vectors in that subspace and add to it, add to this fixed one. So this is, say, my V hat. And then I'm looking at V hat minus W, and W is in the subspace W. That's once again this line only, no? Yeah. In fact, for all you know, this is actually W plus a fixed vector V. And if this vector is in the subspace itself, then this is nothing but the W space itself. Yeah. So this set is the same as W, which means the vectors that are being plugged in here are in fact all possible vectors in W. So then this inequality I can also write, so star is equivalent to star is equivalent to 2 times real part of V minus V hat W tilde plus W tilde square greater than or equal to 0 for all W tilde in W. I hope this makes sense. This follows because in this inequality I was plugging in vectors here of this form for all possible W, but that is the same as plugging in vectors from W. Those are the ones I'm calling W tilde. And I have same vector here. So plugging in vectors here, which are of this form, we had minus W, and W is all possible vectors from the subspace W. That's the same as plugging in all possible arbitrary vectors W tilde from W. That's why star inequality is the same as this inequality. We call this inequality, say, double star. Yeah, is that all right? Now, the question is this inequality possible? Or when is this inequality possible? That is what we will see now. So these W tildes are arbitrary, no? What I'm going to claim now is once again quite non-intuitive, so you have to pay absolute attention. What we will do is we will do the following. Say W in W is arbitrary. Yeah. With this arbitrary W, suppose I define W tilde to be equal to V minus V hat. This is a fixed vector, given fixed vector. Its dot product with inner product with W multiplying W divided by W the norm squared. That is how I'm defining W tilde. Notice that this indeed is a vector in W. This W tilde is in W. So then let us evaluate what this the terms in double star, in the inequality given by double star, those terms, what do they evaluate to for this particular W tilde? So first we notice what happens to this inner product part. What happens to V minus V hat inner product W tilde for this particular W tilde? Then for this W tilde, we get, see, I'm expanding out V hat, and for W tilde, I'm going to write V minus V hat W, yeah, divided by W squared W, like this inner product. Now use sesquilinearity property. This entire scalar will come out with complex conjugation. 1 by W square will be certainly there. That's a positive real number, so its complex conjugation is itself. And then we'll be left with V minus V hat dot product, inner product with W. But then this quantity and this quantity are just complex conjugates of each other. So then this is V minus V hat W magnitude square divided by W squared. This is the fate of the inner product. Okay. What about the second term? W tilde norm squared. This would be V minus V hat W norm squared. This whole thing norm squared. This will be, so let us once again expand this out. This will be V minus, this is a scalar. So homogeneity property would tell me that this norm squared will come out. W to the power 4 will come out and W square will be there. But this and this can be cancelled out. I have just W2, right? Now compare the situation. Here W tilde square and this inner product, they come out to be exactly the same. Okay. Now in this scenario, if they come exactly to be the same, now notice I can do this trick. I define this W tilde with a minus sign here. Yeah, this minus sign will cause this minus sign to appear here, but this minus sign here will not appear. Okay, so then for this W tilde, for W tilde defined as W tilde equal to minus V minus V hat W squared W, where W in W is arbitrary. We get from that the LHS of double star is equal to, what was the LHS? It was 2 times real part of V minus V hat into W tilde. Yeah, double star, where is it? Yeah, W tilde plus W tilde square. What are these? This is minus 2 times, this is the expression, V minus V hat into W magnitude squared divided by W squared plus V minus V hat W squared divided by W squared. But this clearly is less than or equal to 0 and is equal to 0 if and only if V minus V hat W is equal to 0. But then double star says that this quantity minus 2 V minus V hat W square divided by W square plus V minus V hat W square divided by W square. This is bigger than or equal to 0. Look at star. Star says that this is bigger than or equal to 0. Double star is bigger than or equal to 0. So this same quantity has to be bigger than or equal to 0, also has to be less than or equal to 0, which means it has to be 0. But 0 means this has to be 0. And W was arbitrary, so this is true for all W. Right? So this is it. So then what we have essentially what we have shown in this process is that if v hat is a best approximation, then v minus v hat satisfies this property, which means v minus v hat is orthogonal to w. So v minus v hat, the way to write this is that this is orthogonal to the whole space w. This proves the first part. So if and only if a necessary and sufficient condition for a vector to be a best approximation is that the vector, the error, the corresponding error has to be orthogonal to every other vector. Okay, now the second part of this theorem, part 2. What is this? What is the statement of the theorem? It says that if a best approximation exists, say v hat, then v hat is unique. Proof. Once again, very simple proof. Take any other vector. Take any other vector w in w. We have already seen that this is the inequality. V minus w is equal to v minus v hat square plus v hat minus w square. Now, if both v and w are v hat and w are best approximation, suppose both v hat and w are best approximations, yeah, then if both are best approximations, then they have to satisfy that this is equal to v minus v hat. Yeah, whenever it's not equal, the one that is smaller, that will be a best approximation, not the other one. If both of them have to be the best approximations, then they had better be equal. I mean, the error had better be equal. So the errors must be equal. So if the errors are equal, then this implies v hat minus w square must be equal to 0, because this term and this term are equal. This has to be 0. But we know that this is 0 from the property of positive definiteness of norms. This implies v hat minus w is equal to 0, since v equal to 0 if and only if v is equal to 0. That's the property of the norm, right? But this means v hat must be equal to w, so v hat is in fact unique. Very simple. Number 3 is perhaps the most profound. I mean, let's not say profound, but most useful. Okay, so we make this assumption that suppose w is finite dimensional, then by Gram-Schmidt we know that there exists w1 dot 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 up to wn an orthogonal or orthonormal. Let's say orthonormal. Should we do it orthonormal or orthogonal? Orthonormal. Let's keep it orthonormal. Orthonormal basis. W is finite dimensional. Then by Gram-Schmidt there is an orthonormal basis for W. An orthonormal basis for W. Yeah. Then this is not a theorem. This is very simple. This is something that we have already seen. The theorem says that then this best approximation will exist, and because it exists, it will be unique. That guy is actually given by summation I going from 1 to n v wi, this inner product, into wi is the best approximation. Proof, once again, simple. So what we have to do by part 1, we already know that by part 1, it is enough to show that it is enough to show that v minus v hat w is equal to 0 for all w in w. Yeah, is that all right? But you see, this is also enough to show that uh, it is enough to show that because w1 up to wn is a basis for w, it's enough to show that this is equal to 0 for all I equal to 1, 2, 3 up to n. If I show orthogonality with the basis vectors, that's enough, because anything else will be a linear combination of that, and by sesquilinearity, it will just, if I have alpha 1 w1 plus dot 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 up to alpha n wn inner product with v minus vw, then that is the same as summation inner product v minus vw v hat into wi alpha I will come out, right? So this is enough. Okay, now why is this true? Let us just check. No, what is v minus v hat in our case? V minus v hat, okay, v minus v hat is equal to v minus summation I going from 1 to n v wi wi. This wj, if I do now, this wj is what I have to do. But then this is the same as, by linearity, is the same as v minus w, v inner product wj minus summation I going from 1 to n v wi and wi wj. By orthonormality, this is the same as v minus wj minus, all these guys are 0 except for j equal to I situation, or I equal to j rather situation. So this is, and wi and wj is 1 because it's an orthonormal. This is the same as v wj wj since wi wj is equal to delta ij, the Kronecker delta. This is the same as v minus wj minus v minus v inner product wj wj square, but that is equal to 1 because of orthonormality. Then this is 0. This two are the same, so this is equal to 0, which means this is 0. So let w be given as alpha 1 w1 plus dot 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 up to alpha n wn. So this implies v minus v hat w is the same as v minus v hat alpha 1 w1 plus dot 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 alpha n wn. This is the same as alpha 1 bar v minus v hat w1. This is what I was saying, alpha 2 bar v minus v hat w2 plus dot 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 up to alpha n bar v minus v hat into wn. But these are 0, we have already shown. So this is also equal to 0. So this implies v minus v hat the error, w is equal to 0 for all w in w. So the way we have defined v hat, it satisfies that this is orthogonal to all w. So this implies v hat is, now I can say, the best approximation because I have shown that this is unique. Yeah, I've said so many things. Let me repeat what is the crux of the matter. The crux of the matter is that if W subspace is a finite dimensional subspace which has an orthonormal basis, okay, then this is the best approximation because it satisfies the best approximation criterion of orthogonality of the error. Okay, just one simple homework for you. If so, this completes the proof. Huh? So if W1 up to Wn is only orthogonal and not orthonormal, then find out the expression for the best approximation we had. This is your homework problem. Okay. Now this actually ends today's discussion. Yeah. So what we have seen is this idea of inner product. We started with the idea of inner product, which is an extension of the idea of dot product for real numbers for R3. Yeah. And then we have seen that we can draw this abstract definition of inner product for abstract vector spaces defined over real numbers or complex numbers. Yeah, with the help of that, one can get this idea of a norm. Yeah, norm satisfies certain properties, namely two very important inequalities: this the Cauchy-Schwarz inequality and the triangle inequality. And with that, we have seen that with Cauchy-Schwarz inequality, one can define this idea of orthogonality of vectors. That gives us the idea of orthogonal set of vectors. We've seen that orthogonal set implies linearly independent. Then we use Gram-Schmidt orthogonalization to show that a finite dimensional vector space will always have an orthonormal basis. Then with the idea of orthonormal basis, we have seen how one can obtain the best approximation of a given vector V in a possibly infinite dimensional vector space to a finite dimensional subspace. Yeah, with the idea of orthogonal projection. Okay, so this is the end of today's lecture, lecture number 9. In lecture number 10, we'll see, I plan to give 3 examples, but if not possible, then I'll do at least 2 examples where this idea of best approximation is used, yeah, in engineering. And then we'll also see the idea of what is known as the orthogonal complement of a subspace in a finite dimensional vector space. Okay, and how in an inner product space one can always decompose the space, the whole space, into 2 such subspaces, yeah, whose direct sum gives us the whole space. Okay, so I hope you understood what we discussed in this lecture. If there are any difficulties, if you have any questions, then you can either pose those questions as comments on YouTube. But there's a caveat that sometimes you pose these questions, but later on I don't get to see those comments. Maybe there's some issue. So instead, it's a better idea to pose your questions on the Google Classroom stream, or you can directly send me an email. Okay. All right. Then all the best. Take care. Stay safe. Bye-bye.